Hello and welcome to this demonstration. In this video, I will show you how our system models mathematical knowledge using a semi-formal ontology. This ontology is automatically populated using large language model from LaTeX files, and it can be explored interactively via web interface. While the ontology itself isn't the main focus of our work, we developed it because now existing ontologies serve our purpose to showcase its capabilities that design a toy problem ontology with a few definitions and three propositions. The first one assuming that we have a continuous function in a compact interval and concluding that the function is bound. The second one assuming that we have a rational function that has no roots in its denominator, so then we have a continuous function. And the third one assuming that we have a rational function with no roots in the denominator, concluding that we have a bound function. These two problems will help us illustrate the use case of our design ontology. Here you can see the ontology in PoC. On the left, we have the class hierarchy, and on the right, details about the relationships and properties. We can observe the objects that symbol can be mapped to, such as constant, real number, or integer. Then we have definition of these two problem ontologies, such as bound function and compact interval. And finally, we have the three propositions we have commented before. If we click on one of them, we can see the relationships of assumes and implications that this concrete proposition has. Now, let's move on to the web interface. On the knowledge queries page, we can input queries to retrieve definitions similar to the one we are searching for. We can also set the number of similar statements we want to display and the minimum confidence required for a match. For example, let's query for a bounded function with a minimum confidence of 0.6. As you can see, the system accurately retrieves the correct definition. To further demonstrate the functionality, we will reduce the minimum similarity score to 0, as this will allow us to retrieve all definitions within our toy problem ontology. Now, let's dive into the first use case, hypothesis minimization. This use case helps us determine the minimal set of assumptions required to reach a desired conclusion. Imagine we have a set of conclusions we want to derive and a list of known hypotheses or assumptions. The system calculates any additional hypotheses needed to achieve these conclusions. Let's walk through two examples to see how this works in practice. In the first example, our goal is to achieve the conclusion bounded function. We start by specifying this is as our desired conclusion to the system alongside an empty list of initial hypotheses. Now we click on minimize conclusion. And as we can see, the system effectively recognizes that anonymous definition and the rational function are the two required definitions in order to use this proposition, because the other option is proposition 1 that requires the definition of an interval compact and a continuous function, but the continuous function also requires of both, that the function is rational and that the polynomial in the denominator polynomial has no roots in the domain. In the second example, we'll assume we already have continuity as known hypothesis. For this, we will add continuity as an assumption, and now we'll click on minimize hypothesis. We can see that accurately the system indicates that we only need to add the definition of compact interval in order to arrive to the conclusion bound function. The second use case is conclusion maximization. This is the dual of the previous problem. Instead of determining what hypotheses are needed, we start with a set of given hypotheses and compute the maximum number of conclusions derivable from them without adding new assumptions. As a first example, we are going to start with only the assumption that the function is rational. So we add this to the assumption with no implications, and if we click and maximize conclusions, we can see that no result can be derived. But on the other hand, if we add, for example, the anonymous definition, is that the polynomial has no root in the set, and we maximize conclusions, we can check that the proposition 2 and proposition 3 can be used in order to obtain both that the function is bound and that the function is continuous. In addition, if we also add that the interval is compact, maximizing conclusions, we can see that the function is bound, but we have two possible ways. The first one, using proposition 3 that we already have, and also another one using proposition 1 using this path. This is represented with a structure graph that uses Sugiyama frameworks for representation. The final use case is what we call pseudo-proof generation. Here, the goal is to find the shortest logical chain, meaning the path with the fewest intermediate step, to derive desired conclusions from given hypotheses. For this example, we will start from the previous assumptions and we'd like to arrive to the definition of bounded function. In this case, the method should select to use proposition 3 at least as it is the shortest path. If we put bounded definition as an implication, we can see that accurately the system chooses to use proposition 3 for arriving to the definition. But if we remove, for example, the function is rational, now no possible path exists between the assumptions and the implication, as the system indicates without further problem. We would like to emphasize the potential of this proof of concept to enhance the logical consistency of LLM-based agents when discussing mathematics. These agents could leverage any of these algorithms as tools, much like the proof of concept demonstrated with the DBpedia agent. Now, let me show you another exciting feature of our system, the ability to visualize the ontology graph directly on the web interface. In the dedicated section of the page, you can view the graph representation of the ontology. First, selecting the ontology we want to visualize, as well as the labels. We want to filter the individuals. Predicates we want to show, in this case, assumes that or implies that, and one of the two representation algorithms that our interface incorporates. The first one, the Spring algorithms, and the second one, the planar algorithms that we produce a planar graph.